So 111, this problem, I gave it a try. I even wrote down, something for a different case. In this case particularly, your shot is completely horizontal, so you can't just use approximation that we used originally. That's projectile motion. You can't do that. Now, the problem with this is, the problem with this problem is that they give bullet velocity 900 meters per second. And because it's so close to the surface, right, it's shot from the surface in horizontal direction, so it almost remains close, for some time at least. The problem is that this velocity is just too low. Yeah, that's it. It's just too low. Now I'm saying, what do I mean by that? Why do I say it's too low? The thing is that the orbital velocity, when the radius is capital R around Earth, that's at about 30 kilometer per second. And 30 kilometer per second is just much, much bigger than, sorry, it's not 30 kilometer. It's like 11.2 kilometer per second and something upon, so it's like, I don't remember what that was. Yeah, but the thing was, wait, what was that, 30 or what? 11 upon square root 2, that's like 11 basically 11.2 upon 2 times square root 2 or whatever. The point is, it's this velocity, so square root of gm upon r, this thing is so much bigger than this velocity, right? It's just 0.9 kilometer per second, this kilometer per second, yes. This is like 11.2 into 1.4 something upon 2 is like 11.2 to 0.7, which would be, well, 7.84, right? Approximately 8 kilometer per second, which happens to be bigger than this. So this can't hold, right? This bullet can't keep on going around the Earth. It won't happen like that. It will just be dragged down while it's moving, right? So this is the Earth. The bullet is fired like that. Gravity is acting in this direction on the bullet. As soon as it's fired, right, for some time it will go because maybe it's a little more. I mean, its height is a bit more than the ground height. Yes, but think about it. It has to travel like 1 kilometer. Yeah, so it's in 10 upon 9 seconds. Now, the only way to actually make sense of all of this is that the bullet's height must be a little more than what it actually. It's not supposed to be capital R. It's supposed to be slightly more than that, right? That's the only way that we can actually solve this. Okay, so the question is, the rifle was aimed at vertical line on a target located precisely in the northern direction, so somewhere over here, and then fired, assuming the air tracked negligible. We understood that. Find how much off the line. So what do they mean by the line? They mean how much off this vertical line, right? So by that, they basically mean what is the Coriolis effect's shift on this thing. So it will shift because of the Coriolis effect in this direction. So it's into or out of the plane. We don't care. It will shift from this plane, and how much will that shift be? And also in what direction will the bullet hit the target? And then they are saying it's gonna hit the target, which absolutely makes no sense. Why would it hit the target if it has shifted, right? Yeah, the vertical line on the target, of course, located precisely in the northern direction, and then fire. So this makes no sense at all. This is really, really like very poor. This question is just so poorly written. Fine. Yeah, that's just it. Huh? It's really poorly written. And then we'll just say, okay, maybe it's on the ground and this height is something. So, and then it's just 1 kilometer. So 1 upon 6400, that many radians is what this angle is, which, yes, it's almost as if it's flat ground. So the gravity force is acting downwards, basically towards the center, and this is almost flat. So you can think of it as projectile motion, yes, but it should have an initial height for this to actually make any sense because it's fired horizontally, right? Yeah, and I don't get what they mean by it should hit the target. So in what direction will the bullet hit the target? This makes like no sense. Why would it hit the target if it's already not hitting the target, right? This is contradicting. So shot was fired horizontal direction, yes, Latitude is given, the bullet velocity is given, distance from the target is given. Fine, fine, fine. So probably they just want a deflection. That's it. Yeah, I think so. So then let's do it. Let's do it. Okay. So let's think about it. It's 900 meter per second. The distance is 1 kilometer. So just upon that, it's going to be 10 upon 9 seconds. In 10, approximately 10 upon 9 seconds, right? In that much time, this bullet will have gone towards the target if this was not actually moving, right? Yeah, will have gone towards the target. Now, this guy's height, this bullet's height, how much did that change? So, its vertical velocity, what's the final vertical velocity? That will be 10 upon 9 times 10, which is 100 upon 9, so approximately 10 meter per second, which in comparison to 900 meter per second is just so negligible, right? And similarly, its displacement, oh god, that's even smaller than what, I mean, yeah, it's just so small in comparison to this thing. Well, I should not say it's so small, but it's small enough for us to neglect that completely. Yes, right. So the usual projectile motion over here, that's not gonna work. Yeah, this is how it is. It's not going to work. So now what do we do? So we just do, we just find out, the velocity and then multiply it. So yeah, like what was the thing? It was just r dot times 2 omega, sorry, 2 omega naught, right? That's our Coriolis acceleration. Yes, and r dot in this case is pretty much constant because, so this is our radius vector for that initial point or whatever, or maybe like the point of this particle in general, because it's not like really changing all that much. Okay, this thing is phi. Yes, this is the distance traveled by the particle, so it's almost on the surface, right? There's a little bit of height, but then let's not think about that all that much. So it's, yeah, just a bit of distance that it travels. So then our small r, that's the distance from here to here, but along the xy plane, right? Completely. What will that be? That will just be r cosine phi minus x sine phi. Now why sine phi? It's supposed to be 90 minus phi over here. That's why x sine phi. Phi doesn't change all that much, right? What's 1 upon 64 more radian? And it's not really that big a deal when it's already supposed to be 60 degrees, right? Yeah. But seriously, like, what is 1 upon 64 radians? Whatever. Never mind. 60 degrees is 2 pi upon 3, which is, it's a big number, I guess, in comparison to this small delta phi. Anyway, thing is, sine phi doesn't change all that much. This x thing, right? It's increasing at the rate of the velocity, basically, right? Yeah. Cool. Because the horizontal velocity is fixed anyway, but then we are approximate the vertical velocity to be 0. Yeah, basically yeah, you get the idea, right? And then there is this vertical velocity which also causes a little bit of change in this small r value, yes, but we'll neglect that. Then what that means is, well, dr upon dt is just negative v sine phi. And d squared c upon dt squared, where c is the Coriolis effect's shift, so shift due to Coriolis effect, that is just 2 omega naught times r dot. And r dot is just r upon dt, which is basically this thing. So the magnitude wise, it should just be this thing, sine phi, whatever. That should make sense. Yeah. Yes, I think that makes sense. Okay. And now this is almost constant. This is almost constant. This is almost constant. So what do we do? It's like constant acceleration, basically, right? So it's gonna be half over that's gone in that case. So that 2 is gone. So like omega naught b sine phi, which is this thing, times t squared. So the time required for it to go from here to here, that will just be whatever distance they gave us. So they gave the distance as s, I think, s upon the velocity, and this thing squared. I know it's just a lot of approximation, and it looks very unnatural, right? But yeah, just have to do it somehow. Oh, come on. First of all, you can clearly see it cannot be shot from the ground itself, but the actual h value that it should be shot from is so small, we can almost neglect it, right? Yeah, right? Throughout the motion, we just neglect the small h value. So why not just neglect, why not just add that small h value at the beginning itself, huh? Right? So that actually it does try to hit at least. And of course it will get deviated, so it won't hit, but it will actually try to hit, right? Cool. So this thing is the shift. Now, what they ask is how much off the line will it hit? Yes, we can figure that out. And in what direction will the bullet hit the target? I don't know. Maybe like you just mean the target will change or something. So what direction you say, huh? But mostly it's just this direction. V is, yeah, it's just this. So what's the big deal about it? Most of the velocity is just in this direction. The other velocity, this component of it and this component of it, those components are small. You don't have to worry about them. So we just present this as the answer and we'll forget about this other question because frankly it doesn't make any sense. How can it hit the target? And if your target is it's changed. Now it's just the wherever it hits, that would be the target if that's what they mean. Uh, and they want to find the velocity, but the velocity is just the same thing as v. So I don't know. I don't know why they are talking about this. Cool. This is it. Right. So this quantity is our answer, I guess. Yes, I already tried till 117. I mean, at least I tried doing how much I could do. Uh, it was really hard because I knew nothing about Coriolis force anyway, right? It's not in my syllabus, the syllabus for the institute that I'm in. It doesn't have that in our syllabus. So instead, I had to go on the net looking for things, and it was just really painful. I had to derive stuff on my own, see if it actually is correct, and throughout the verification process of verifying whether or not what I derived is correct, there was just so many roadblocks. I wish I had not actually looked into this matter and just let it be. But hey, I am me. I do that. Okay, so now we got the answer. 111. Let's calculate this thing. Actually, first of all, just write it down. So omega naught be sine alpha, sorry, sine phi. Phi is the latitude, and then you got this s. This s is not supposed to be sine of anything. It's just the displacement. You know what is called in d instead. So d squared, and then that upon v squared. So instead, we'll just write v right here. So that should do it. Now let's calculate this thing. So sine of 60 degrees is just square root 3 upon 2. Omega naught, we don't, actually I do know, right? Yes, we know it's just 2 into 10 power. It was negative 7, I guess. That's, yeah, 2 into 10 power negative 7. I think that was how it was, right? Approximately, of course. And then you got this times d squared. So the distance is just 1 kilometer. In part 3, that thing was 10 power 6. And that upon the velocity. This should be in SI units or what? Yeah, it should be in SI. I think it was in SI units. They didn't give us what omega naught is, but I remember what this value actually was. So we'll just put that in there. Next got this times 10 power 6. And now this upon the velocity. So velocity was 900 meter per second. So like 9 to 10 power 2. Cool. Let's calculate this thing. So got 10 power 4 over here. Should be 10 power negative 3. These two cancels. You got square root 3 upon 9 into 10 power negative 3 approximately. Wow. This is horrible. This is like really horrible. Because square root 3. Fine, let's do it. Square root 3 is approximately 1.7 something, right? So 1.71, I guess. No, it was not 1.71. It was something else. This 1.7 is good enough, I think. 6 upon 9 is, so it's approximately 2, 0.2, I think. Yeah? 17 upon 9, slightly more than 17 upon 9. 17 upon 9 is anyway just 1.17 and then divided by 9 is supposed to be 1.9, and then point. So 72, you would need 8 for that. 72. Actually, it's like very close to 81, so 1.9 is a good approximation. which is, I mean, it's just better if I use 2 instead. So yeah, 2 into, well, it's supposed to be 10 power 81, and then that's 10 power 84. This is the thing. So this is in meters. This is like really small. This value is in centimeters. Wait, sorry. It's like 0.2 meters. No, this is just too small. That can't be. D squared and D was. Oh, sorry. What? Why did it put 10 power 8? Okay, this is what went wrong. Ah, sorry. 2 to 10 power negative 7 and then power 6. And then this is not. Wait, no, it's actually correct. It should be correct. So, 3.9 to 10 power negative 3. That should be the thing. Unless, of course, this is not the actual value, which is probably what happened. Come on. I don't know. This is less. It's like really, really small. Why? Why is it so small? So square root 3 upon the sine phi, and that times omega naught. Oh, come on. I don't. You know what? Maybe it's better if I just verify what omega naught should be. So go to Google. Yes, we'll go to Google now. So what do I want? Yeah, angular velocity. So Earth angular velocity, right? So the angular speed of the Earth is in inertial space. What does that even mean? Each many radian per second. Okay. So it's 7.29 plus minus 0. Okay, that's not important. So it's 7.3 approximately. 7.3 to 10 power negative 5. That's how it should be. Wait, what? Is that for real? But I remember I read it to be 2 to 10 power negative 7 somewhere. Oh, come on. So which value is more reliable? I don't know. What? Okay, not interested. Yes, but they are saying it's 7.29 whatever into 10 power negative 5 radians per second. So in assignments, it's just 7.2 to 10 power negative 5. Should be working, I guess. So we'll just put that in there. So get rid of all of this. Yes. So for putting omega naught, what was I going to do? Oh, come on, what was I doing? Yes, calculating this thing. So we'll get rid of all of this. So it's got 3 upon 2 omega naught is, so we just got it 7.3 10 power 85, then times t squared, so it's 10 power 6, and that upon velocity is 10 power 2. This is of course much lower than what we initially got. So it's 10 power, sorry, it's much bigger than what we initially got because 10 power 85. What am I doing today? So 10 power 4 and suppose 10 power 81, and that times, well, yeah, square root 3 upon 2 into 7.3, that should do it. So this is like 1.7 something into so 0. What's this? 3515365. Oh, sorry. This should work. Yeah. Is this 1. Okay, fine. And this is going to be in meters. So it's some little meters away. That's still just horrible. 365. That's a nice number. Yes, but this is still just bad because this thing is in kilometers and this thing is in meters, and even after all of these approximations, we are not still getting a big difference. Actually, it's expected for it to be not a big difference, but still, in comparison to 1 kilometer, this thing is just minuscule. It should have been at least some, I don't know, like 5 meters or something like that. This thing is not what I was hoping to get. No, this shouldn't work. What's this? Why? Okay, so they have what was it once again? Where did that 10 power 6 come from? Yeah, s is equal to 10. Was s equal to 10 power 3. That's why 10 power 6 s squared, right? Well, it is what it is. We'll just put that as the answer. I mean, it's just a textbook question. It holds no real significance to what is actually happening with this projectile, right? If it is, I mean, short like, of course there's air drag. Of course, it's not perfectly round. Of course, that small edge does interfere, right? All of this is just approximation, and then we'll approximate this product as well because significant figures and everything. So you can't have it in this kind of precision. It should be round off. Now let's do it. So 365 into 1.7, I guess. So it's something like 5, 3 carried on, supposed to be 40 to 40 minutes of 5. So 4 carried on for 21, 21 and 4 just to 5. Then we got 0 and 365 out here. So 5, 0, 1 carried on, supposed to be 6, 2, 1 carried on, 3, 3, 6, 6, 2, 5. And then how many zeros? 4 zeros. So 1, 2, 3, 4, 0.62 something. So 0.62. In fact, 0.6. That should do it. Those many meters. So basically, 60 centimeter in comparison to the kilometer. This is just no, 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 no. It's not good. Wait, maybe the centrifugal force is important over here. Okay, just don't think about it that much. It's about 0.62 and that's it. Don't go into it. Okay, let's go to 12. Oh, sorry, 111 and then 112, not 12. Horizontal disk rotates with a constant angular velocity, omega is equal to 6 radians per second, about a vertical axis passing through its center. Okay, disk rotating, fine. A small body of mass, something moves along a diameter of the disk. Okay. With a velocity v dash is equal to 5 centimeter per second, which is constant relative to the disk. Cool. Find the force that the disk exerts on the body at the moment when it is located at the distance r is equal to 3 centimeters from the rotation axis. So this force has to be measured in the space at rest, right? Yeah. So the only force that is exerted on this thing in the xy plane, that's because of the disk, right? But that's also the normal force, yes. Just keeping it up. But other than that, it's just xy force. That's completely from the. I mean, it's yeah, gravity and normal force cancel, but the xy force is only from the disk itself. Anyway, what we have is so it's rotating at a constant angular velocity. Body moves along a diameter with a velocity this thing which is constant relative to the disk. That's important, all right. Find the force that the disk exerts on the body at the moment when it is located at the distance r is equal to 30 centimeter. Because the radius and everything. Fine. So what do we use over here? The polar acceleration, that thing. So acceleration polar coordinates. We could use that, right? I think that will be sufficient because yeah, along the time it's like it's dug out or something, and then this is moving along it. So this whole thing is also moving with omega. So this guy's angular velocity about this axis is also just omega. Cool. That means we can just we found out everything over it. Just find the acceleration. So acceleration will be, let's see, what was that once again? R double dot minus r omega squared, and that times r hat. So this is in the radial direction. Then yeah. Was this plus or minus? I think it was plus. So plus 2 omega r dot of that thing, and then it's supposed to be r alpha, I think. And it's either plus or minus, I don't know. I think it's supposed to be plus t hat. Yeah, because what was this like? Yes, it should be just that. There's only one negative when we do the whole thing, and then everything else is either having an iota with it or positive real number. This is the only negative thing we get, and that's why this thing, because iota times r vector, that's just t hat. Yeah, that should do it. So you got the acceleration. Uh, just find the magnitude of this acceleration. So mass is given, whatever. Velocity, if you know what that is, so that's just r dot. But r double dot is just zero because velocity doesn't change. Your angular acceleration is also zero because this is rotating at a constant angular velocity. You definitely have r dot, you have omega, you have r omega squared, yes. So this will just have what magnitude? It's supposed to be omega square root of r omega squared plus 4r dot squared, I think. Yeah, yeah. Yes, that's our angular velocity. So mass times this, sorry, this is our acceleration. So mass times that, that's the thing. Wait, you just want the force. You don't want do you want it? Do you want, what was it considering? Uh, you want the direction? No, I don't think so. Okay, so let's do it. At the moment when it is located at a distance, so r is given, omega is constant anyway, v dot is just the velocity that they gave us, so it's doable. Fine, figure out what this thing is. So omega is, actually, you know what, just write it like that. Hey, and we also should account for the normal force because it's a horizontal disk. So this is also the normal force. Or do we actually consider gravity or not? They didn't tell us that. Because if there's gravity, it's supposed to put a normal force on it and huh. Okay, I'll just say it's not having the normal force because it's gravity free space. They didn't tell anything. So I'll just say it's gravity free. Fine. In that case, this is the force. So our acceleration vector, let's write that down. Or maybe not. Maybe not. So our force is as a magnitude. It's just m omega square root of r omega squared plus 4 velocity squared. So I should say v dash because that's what we should put in there. Cool. So this will be, oh, and okay, so r dot is actually negative v dash. Yeah, whatever, fine. Squared, right? So what is going to be? M is, what's the mass of this guy? 0.5, 1 upon 2, and then omega is 6 square root of r omega. What's r? What is r? 30 centimeters, like 0.3 meters. 0.3 times this thing is supposed to be 1.8. So 1.8 squared plus, so basically 2 v dash squared, right? So what's v dash? 50 centimeters. So 2 times that is just 100 centimeters per second. It's like 1 meter per second. So that thing is just 1. Everything is in SI units. Cool. So 3 square root of 1 plus 3.24. It's supposed to be 3 square root of 4.24. Huh. Fine. So 6 square root of 1.06. Now, wait, have I seen this somewhere already? I don't know. Okay, whatever. Yeah, this is the thing. So it's gonna be 6 and 1 minus, no, so plus half 0.06 approximately. So 0.03. And I think it's a damn good approximation because the other terms, they're so small, you can ignore them, right? 0.06 squared, come on, that's minuscule. So there we go. It is going to be 6.18. Yeah, that should be the thing. So this whole thing is just 6.18 newtons along the xy plane, on the xy plane. We don't know anything about the vertical motion, so the vertical force is on this plane. 113. But I mean, okay, when it says horizontal, it's horizontal with respect to what? What's maybe it does have gravity. I don't know. Just leave it like that. 113. A horizontal smooth rod AB rotates with a constant angular velocity about a vertical axis passing through its end A. Okay. Smooth rod AB. Where is AB? A. Wait. Okay, this figure is not for that. Sorry. Right. So AB rotates with constant angular velocity about a vertical axis passing through its end A. This is AB. Its omega is given. And then what? A freely sliding sleeve of mass m is equal to 0.5 kg moves along the rod from the point A with the initial velocity v naught is equal to 1 meter per second. Oh, so it's like this. It's okay, cool. Find the Coriolis force acting on the sleeve in the reference frame fixed to the rotating rod. Cool. So good thing. Yeah. So the thing is, this is the first page of my derivation. This is in the first page that when this is not rotating with respect to the rotating frame, all you have to do is, yeah, I mean, then it just becomes the centrifugal force and Coriolis force and all that stuff. So there's centrifugal force in this direction. There's also the Coriolis force, which is in I don't know. I don't remember its direction. No, it's along the negative I hat. Yes. So it's towards us basically. If omega is like this, then it's towards us. Okay. And which is basically just 2 omega r dot and that times m. That's our Coriolis force and the Euler force. So there's r alpha because of that. But the good thing is over here alpha is no, it's not here. So move that. It's just the Coriolis force acting on. And there's centrifugal force, of course. What we want is find the Coriolis force acting on the sleeve in the reference frame with fixed rotating rod. And at the moment when the sleeve is rotated at distance r is equal to 50 centimeters from the rotational axis. So the thing is we need r dot for that. So we need to figure out how does this velocity change. Now, there's only one thing that can change its velocity, which is the centrifugal force. It's gonna be omega squared r. That's what acceleration basically. That's equal to the, yeah, it's supposed to be d squared r upon dt squared. Yes, that should make sense. Or you can just go with v dv upon dr, right? Yeah. So v dv is, so oh sorry, it should just be integrated already. So v squared upon 2 as it goes from somewhere to somewhere, and we can get rid of these 2's as well actually. So as it goes from v naught to, I don't know, whatever velocity it has, is equal to omega squared r squared. So r initially was 0. That's why it's r squared. So v squared minus v naught squared is equal to omega squared r squared. Cool. And what we want is the Coriolis force, which is just 2m omega, and then the velocity. Yeah. In this particular case, the velocity is the same thing as r dot. Usually it's not, but here it is. And then there's the general case where you actually have put omega naught, right? But it's not the general case. It's the front page of my full derivation that I did. Really, you should check that out because there I did it in full detail. Over here, it's not possible to do it in full detail. Now, what do we want? We just want the v thing. So put that over here, v naught squared and square root. Cool. Just put that in there. This should do it. Cancel all of this. So force will just be 2m omega and then square root of all of this, omega squared r squared plus v naught squared. Now let's calculate this thing. 2 times of the mass is it's 113, right? Okay, omega is 2 radians, whatever. So 2 times 2 is 4, and the mass is 0.5. Good. This times that cancels. So just 2. 2 square root of now 1 upon 2 times r. So r is 50 centimeters. What? Are you serious? So it's like half a meter. Oh. Okay, so it's 1/4 squared. Oh, this is bad. Oh, sorry, no. Omega is 2. What am I doing? It's just 1 squared. Yes, it's just 1 squared and then plus v naught. V naught is also 1, so just that. So 2 square root 2 in SI units. Cool. So this will be 2 square root 2 in SI units, which is Coriolis force, right? So it's newtons. 114. Horizontal disk of radius capital R rotates with constant angular velocity omega about a stationary vertical axis passing through its edge. Okay, disk passing through its edge. Oh, so like if this is a top view, then it's rotating about this thing. Okay. Along the circumference of the disk, a particle of mass small m moves with velocity that is constant related to the disk. Oh, okay, fine. At the moment when the particle is at maximum distance from the rotation axis, the resultant of the inertial forces in the reference frame fixed to the disk. Oh, so Huh. Okay. Of the inertial forces Fn acting on the particle. Wait, inertial forces. Wait, but this doesn't make sense because how do you distinguish between inertial forces and non-inertial ones? Okay, how do I do that? So, for example, is centrifugal force an inertial force? So, when you go through a path, does the work done depend on the path? Actually, no, it's just radially outward everywhere. So, in that particular frame, it's not inertial. It's almost the same thing as the force put on by a point charge, another point charge, right? Something like that. Yes, just proportional to r in that case. Yeah. So I don't think that our centrifugal force is non-inertial. That's not the case. Okay. Wait. Okay. You are saying the resultant of the inertial forces is zero. Huh. What else do you have? You also have the Coriolis force. So that's dependent on v dot, unfortunately. Sorry, r dot. So that's dependent on the velocity basically, and or not on the path itself. That's a problematic thing, right? Sorry, it's not dependent on the position itself. It's dependent on the velocity. So that r dot thing. Oh, okay, that's problematic. Yeah, so it's not inertial in that case. So Coriolis force is not inertial. It's bad. What about the Euler force, that is R alpha? So in this particular case, alpha is zero, so you don't have to worry about it at all. Mhm. Sorry, it should be R alpha not, but yeah, it's zero. And then there's the proper centripetal acceleration on this guy. Yes. Uh, oh, come on. Okay. So that force is also there. There's a centripetal force, there's a centripetal force in this frame. Yes. So centripetal forces, I think it's also just it's the actual force, right? So is that inertial or not? I don't know. I mean, it's not like it's not force from actual force analysis. It's just acceleration times mass. It's supposed to be this normal force acting on this guy. This is so bad. How do I know what is inertial and what not? Is there a test for this or something? The net force as seen from this is just acceleration times mass. Yes, but it's not from the force analysis. So do we take that into account? I mean, that force minus the centrifugal force, that will be the remaining force you can think. And well, that contains the Coriolis force and everything. Yes. Ah. Oh wait, no. This is really bad. Find the acceleration of the particle relative to the disk. At that particular moment, you say, uh, of the inertial forces acting on the part. Is this, what do I make of it? Okay, A doesn't look that bad, so it's just related to the disk of the particle, right? So it's constant angular velocity. This is awesome. It's just going to be a centripetal acceleration with respect to the disk, of course. Yes. The dependence of Fn on the distance from the rotation axis. Uh, what? Okay, you know what? I don't understand what this is supposed to be. Just leave it, right? So I will do A, I won't do B. Uh, why can't I stop thinking about it? Centrifugal forces. You can't do proper force analysis of it. That's the main problem. Those pseudo forces, those must be balanced up, I guess. No, no, no. The pseudo forces, they Centrifugal force is actually, I know it's inertial, yes. Other than that, the other forces are not inertial. Actually, no, the R alpha force is in fact inertial, right? Because it's along that end. Okay, no, R alpha force is not inertial because if you go, so yeah, if this is your point, I don't know. Think about a completely different scenario. This is the rotating frame. On this, there's this point R alpha is in the tangential direction, right? Wait, no, 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 no. That's wrong. That can't be. Oh, and moreover, this thing is actually not fixed, so it's moving, and I have to apply the general formula for this thing, and okay, that makes it just, oh god, I'm not gonna do it, right? So I'm not going to do it because I don't even remember the whole formula for that. Yeah, it contains too many terms to remember. Okay, so 114, I'll just do A. The acceleration of the particle relative to the disk. That's very straightforward. It's gonna be omega squared upon omega squared r, right? Wait, the disk rotates with omega, and a stationary. Okay, what's this? And moving through its edge along its constant. Wait. You're saying it has a velocity this constant. Wait, sorry, I misinterpreted this then. In that case, I thought it was at a constant angular velocity. Wait, okay, no, it is at a constant angular. Sorry. Along the circumference of the disk, a particle of m moves with a velocity that is constant related to the disk. Of course, it has constant angular velocity. So a is still just v squared upon the radius of the disk, right? Related to the disk, you got what the acceleration should be. Yes. So I don't know what b is and how to do it. Let's go to 115. A small body of mass something starts sliding down from the top of the smooth sphere radius something. The sphere rotates with a constant angular velocity omega about a vertical axis passing through its center. Oh no, I think it's bad news. Find the centrifugal force. So it's a smooth thing. Okay, that's nice. Oh no. Centrifugal force of inertia and the Coriolis force at the moment when the body breaks off the surface of the sphere in the reference frame fixed to the sphere. Ah, what? How much worse could this have been? Ah, come on. You see this. So, uh, fine. So we'll have to use the standard textbook definitions of Coriolis force for this thing because it's 3D and everything's just going really problematic for even because it's not matching up. It's omega is different and everything. Uh, yeah, so you have to do that. I mean, the previous question where we had to use the Coriolis force, so the Earth question, the angular velocity of that particle with respect to Earth was fairly constant, right? So it was, yeah, about the axis, of course. It was almost constant, just deviating slightly. In this case, it's not the case anymore. It's very different. How do we do this? So there's supposed to be an Euler force as well, and then there's Coriolis force. Centrifugal force will be probably the easiest to figure out. No, it won't be. Come on, it won't be. Because it's rotating in 3D actually. Wait a second. Okay, if this is a constant, so it's just basically like, oh yeah, this particle has nothing to do with the sphere. It just goes down like that, not caring where the sphere is rotating or not. Fine, but according to sphere, it does matter whether or not it's rotating. Oh come on. because omega is not fixed, whatever. Oh, this is just will get bad. So you can figure out what the actual centripetal force on this is. Yes, you can do the analysis in the the space frame. But when you go to this guy, oh, this is gonna get so ugly. I will have to use those things that supposed to be 2m. So the Coriolis force is just omega vector. I know. I I never actually explained that there's a formula for this thing. And the thing is, the whole derivation I didn't actually label what the Coriolis force is for the general case. Actually, the Coriolis force is this thing. I never told you this because I found this to be unimportant, right? Because it only, I mean, is useful when actually you can calculate it, right? And do something with it. But when it was the general case, it was not turning out to be useful. So I just dissolved this. But in this case, it's not gonna work like that. Fine. The good thing is like omega is just upwards, so all of the upward component you can just remove that, right? So this velocity vector, it's only the xy component that we actually have to deal with. So the xy component, moreover, is just whatever velocity this thing has, the component in this component going in that direction. So omega cross that thing, that's always in this direction basically. Wait, what? Omega is in, okay, so if omega is like that and this is how it is, so omega must be, also it should be in, sorry, this direction, whatever. Yeah, you get that. Fine. That's our Coriolis force. Then there's our centrifugal force as well. So it's m omega squared r. Yeah, but actually it's different from that, I guess. It was something like m omega vector cross omega vector cross r, I think. Yeah, there was a centrifugal force. Only like negative of that. Oof. Okay, now I just don't remember what was happening. Just like omega dot r, usually it would be 0. In this case, actually, as well, it's going to be 0 because we just take r to be this thing. So good. Then, yeah, you could just go with omega squared r. Which makes sense. Oof. Okay, that's that centrifugal force. And yeah, I mean, the radial component that I did in my derivation, it contained the centrifugal force plus some part of the Coriolis force as well, right? And that part, that's not a part of the centrifugal acceleration, but it just helps write it like that because now you got a radial and a tangential component. So that's how we will use it in actual problems, not in problems like these. In these problems, you have to use the definition. Okay, so this is still omega squared r, omega squared r in this direction. Cool. You also have the Euler force, but then acceleration. So angular acceleration of uh, this rotating frame is 0, so you don't have to worry about that actually. Yeah, cool. And yeah, this is our pseudo forces. All of these pseudo forces really. So it's just negative iota times all of that. Okay, come on, don't use complex number in this case. Yeah. Ah, this is so bad. It really was negative, right? Or was it positive? I don't know. What do you want to find? Find the centrifugal force of inertia and the Coriolis force of the at the moment when the, so we just want the magnitudes anyway, so don't worry about that. And because like these are perpendicular, actually it's just going to be omega and then dr upon dt, so r dot. So that's the only component of the velocity we actually use. So you got that at least. Cool. And yeah, because it's just going down, you can figure out how it goes down, the equations of motion for that in the space frame. And then from that, you can figure out what r dot should be. So you want it at the moment when the body breaks off. So you have to do it the proper way. Okay. So this is our sphere on which it's rotating. right? So it starts off from here, it's going like that. If this has velocity, or let's just say it's at omega. So this whole thing, we'll call this as the x-axis and this as the y-axis. I know, very unconventional, but we'll call it like that. It's phi, sorry, theta. Theta is better. So then, if this is has to be a real axis, this is the imaginary axis. This will be e bar I theta. There's the gravity acting on it, right? Gravity is always in this direction, and there's a normal force acting on it. Or you could just not think about it as complex numbers, right? There's gravity acting on it, and some component of the gravity is acting in this direction. Normal force is computed in that direction, so it's not accelerating it. But tangential acceleration is really just, what is it? Oh, and also you will need centripetal acceleration for this to happen. Fine. First of all, let's figure out what this is. This angle is supposed to be theta, is supposed to be 9 theta, so g cosine of that is supposed to be g sine theta. Okay. Do you know the centripetal acceleration? So v squared upon r. So v is just the v tangential, which is, I mean, yeah, it's always tangential anyway. It's just v squared upon r is equal to the gravity force, yes. So the gravity acceleration, sorry. So g cosine theta, it's very weird. It's whatever. And then minus the normal force upon the mass. That should do it. So for the critical condition, this normal force becomes 0. That is, it can no longer hold. Yeah. The like the gravity force is not sufficient anymore. That's when this will break off. So for that particular case, can you just figure out, okay, this is useful, I guess. So tangential acceleration, you can just think of it as r alpha. And this thing, you can think of it as omega squared r. Cool. So this thing is actually not so useful because normal is a variable. This thing is very useful. So sine theta, huh? So r omega, so just integrating it till time. Oh no, it's gonna be really bad. Gotta think of something else. So you just need omega actually. So you can just use this to figure out omega and theta relationship. So r omega d omega is equal to g sine theta d theta. Right, and theta is increasing as well, so it works out. So it's gonna be r omega squared upon 2. Initially it's at 0, I think. Wait, okay, this what? 115, right? Start sliding down. So yeah, it's 0. So just r omega squared upon 2 is equal to, so integration of this thing, just negative g cosine theta. Oh god, okay, theta is equal to 0. This is really bad. Okay, just do it. G into 1 minus cosine theta. This is the thing. So now you know what omega squared r should be. Just put that in here and we'll see what we get. Yeah, I mean, you figure out what the omega should be and everything. What we actually are looking for are these two forces. Oh yeah, so what's r dot? R dot is this is really bad. Yeah, it's really bad. Let's try it. So r dot is just derivative of, what am I doing? Of, well, r, yeah, it's like small r is just r sine theta, right? So that's going to be r cosine theta, and then that times omega. We need to figure out what this is to actually get anything. Yeah, and then you also need to figure out what the omega should be. So our goals are to figure out omega and this quantity. So first of all, we have to figure out a theta for this. So putting this into here, and putting normal is equal to 0. All you get is just 2g cosine theta is equal to g cosine theta. So this thing is gone. Perfect. 2 is equal to, well, 3 cosine theta. So cosine theta is just 2/3. Nice. Once you know that, you can figure out what this should be. Yeah. So r omega squared is, so 2g into 1 minus 2/3 is just 2g upon 3. Yeah, this is another thing we know. So at that breaking point, this happens and this happens, and r dot in that case will be, or in fact, let's not use that. Yeah, this is all we really need. So we can get rid of everything else. Now let's go to our main problem. First, we'll need what omega r dot is. So omega r dot is just r cosine theta omega squared, and then r omega squared, you already know what that is. It's just 2g upon 3, and that times cosine theta is just 2/3, so 4g upon 9. We got what this part is, so just that times 2, so 8g upon 9 times m. So this is the magnitude of this, right? I'll just remove that, whatever. Yeah, that's just 8 ng upon 9. That should work. What about this guy, m omega squared r? So you already, yeah, omega squared small r. Yes. You know what capital R omega squared is? That's not what we're looking for. Wait. This omega and that, aren't these two different? Oh no. Oh no. This is bad. That omega, okay, I should just label this as omega naught, so that they don't confuse what is going on. So this is not correct. Sorry. This is incorrect. Okay. So r dot, you just have to figure it out actually. Ah, you'll have to calculate this. Are you serious? Okay. So how do you, what was this? Yeah, whatever. What's this thing? So these are equations. Oh, come on. So what's omega going to be? The square root of 2g upon 3r. So r dot is just r square root of 2g upon 3r, and that times cosine theta is like 2/3. Yes. So this will be square root of 4 upon, oh no, it's supposed to be 2 squared, and it's like 8 upon 27. Or you can just put 2/3 power of 3 upon 2, that might be better. What's happening? 2/3 power 3 upon 2, and then you got square root of rg. Okay, so that's r dot. Just need to put that in here. So 2m omega naught, and then r dot. So that's going to be 2/3 power 3 upon 2 square root of rg. This thing is our Coriolis force, and our that thing, right? The, what was it once again? Centrifugal force, right? So oh come on, both of these are the same things, right? This is Coriolis and centrifugal. It's just omega naught squared r times m, right? So m omega naught squared, and well, small r, which, I mean, it's not that hard. Small r will just be, yeah, it's capital R sine theta, and then this is 2/3. Okay, this is bad. Square root of 1/3, huh? Oh, come on. So all of us upon square root 3, and then you just got capital R. Okay. Hey, this is what, did they put A or B? No. Okay, that should do it. Good. So let's write down Coriolis. What's the spelling? Oh, it's supposed to be I. Coriolis force is equal to, just write this in there, 2m, oh my god, just copy this actually. There we go. So this is the thing. Coriolis force is just that. Minimize this. Well, this should do it. And what else were we looking for? The centrifugal force. Centrifugal force is equal to m omega naught squared r upon 3. Sorry, square root 3. Yes, this should do it. Now, should I actually calculate this? Oh, it's just uh, r is 1, thank god. And then square root of g. Oh, come on. Serious. Omega naught is 0.3. So yeah, that's mass. Okay, that's 0.3 and omega is given is to 6. Fine, let's calculate. So first we'll just start out from centrifugal force. This is going to be m, which is 0.3 into omega naught squared. So omega is 6. It's like 36. That times the radius, which is 1. So forget about that. Square root 3 over here. It's going to be 3.6 square root 3, right? So this will be 3.6 square root 3 for this case. And this whole thing, yes. So 2m is just 12 because it was 6, right? Yeah. No, okay, mass was 0.3, sorry. It's supposed to be 0.6 in that case. 0.6 and then omega naught, which is 6. Okay. 2/3 power 3 upon 2 is like 2/3 square root of 2 upon 3, and then you got square root of r, which is square root of. So r is 1, so it's just square root of g. And g equal to 10 probably won't work. 9.8, yeah, you can go with that. That's better. So this will be, this is 3, so like 0.2. So 0.2 times 6 is what it is. 0, okay, 1.2. 1.2 times 2 is 2.4. So 2.4, you got square root 3 in the denominator. Wow. Why? But you have it. And then square root of, so this 2 comes inside, and then it just becomes square root of, yeah, becomes of that. It's like 2 times 2 into 4.9. That should be nice. Oh, come on, it's 9.8. That's just really hard to figure out. 9, I mean, why? 9.8. If it was 49, it would be so much better, but this, no, it's not. Okay, gotta do it like that. It's upon 3. So it's 2.4 into 7 into square root of 0.4 upon 3, which is 0.1333. Okay, no, not nice. 0.1333. Close to 0.121, I guess. Then 12 square is 0.144. Which of them is closer? I think 0.121. So you can take that 11 out, or you could just do the square root normally. Hey, come on. I mean, over here, just put that square root 3 like that. So why not just keep it like that, huh? Yeah. Square root of 0.4 upon 3 is like 4 upon 30 or whatever. So 2 upon 15. Oh, we could actually even get rid of that thing. So scrap that. 2.4 is just 0.8 into 3. So 0.8 into 7 into square root of 1.2, which is close to 1.21. So 0.1, no, wait. Yeah, it's close to 0.121. So 1.1 squared, which is just 1.21, but with 2 decimals, this is like 1. Yeah, 1.21. So that's close enough, I guess. So this is approximately 0.827 into 1.1. That should do it. So that will be 0.8 into 7 into 1.1, which is 0.56 into 11, I think. So 56 over here is supposed to be 6.16. That's how much it is. So yeah, this is, okay, where do I write it? This is approximately 6.16. No, I'm gonna do this thing. Next question, 116. A train of mass something tons moves in the latitude north. Okay, find the magnitude direction of the lateral force that the train exerts on the rails if it moves along a meridian with velocity this. Oh, hey, the good thing is that this guy's angular velocity about the central axis is not changing, right? Yeah, it's not just consideration of angular momentum. That's not gonna happen, right? So you don't have to worry about that thing happening. There's friction and everything. So it's just, yeah, it's not actual dynamics. It's just kinematics basically, kind of like that, right? Because you're just dealing with accelerations and multiplying by mass. It's not really force analysis. Magnitude and direction of the lateral force that the train exerts on the rails. So lateral force. Oh, so yeah, like this is the train. These are the train tracks. The train is over here. There's some Coriolis force acting on this thing. So the same force must act on that, and the opposite force acts on this. So it doesn't go like that. Yeah. And then this force acting on the ground, it doesn't really change a lot of the properties of Earth because Earth is so big. Yeah. Mm-hmm. Kind of a direction of the lateral force that the train exerts on the rail if it moves along the meridian. So along the meridian, good. Then it's along either north or south direction. Velocity is given. Okay, in what direction, what velocity the train should move for the resultant of the inertial forces acting on the train in the reference frame fixed to Earth to be equal to zero. Huh? Once again, the same thing about like inertial forces and whatnot. I don't know, right? I'll just do A and then we'll move on. Okay, so yeah, I mean, you remember what I did with the projectile motion thing, that derivation? Yeah, the tangential acceleration. So I said it to be tangential. It's like T hat, along T hat. If you don't know what I'm talking about, just watch that video. It will make my job much easier. So it's just T hat, right? Along that, the acceleration, the pseudo acceleration, I should say. So the Coriolis force is just 2m omega r dot, and then the acceleration was just this thing, right? And really, we just need to find the force. So this thing, that pseudo force of Coriolis, and that pseudo Coriolis force is acting on strain as seen from the Earth. Then, of course, some other force must be acting on it to balance it. All the other forces, the other pseudo forces, that is, those were just acting on the meridian's plane, right? Yeah, and this is only the one that is acting normal to the meridian. So that's a lateral force. Yes. Okay. So what's R dot? Uh, yeah, like R is just capital R cosine phi, I think, right? This thing is how it goes. So this is R, and this thing is a small r, and this is rotating about that whatever. It's rotating at omega naught. Okay, let's use omega naught. Yeah, so capital R cosine phi, that's whatever small r is. And we just take a derivative of this thing. So R dot is just, what was I gonna do? Negative R sine phi, whatever, d phi upon dt. And we just talk about magnitude. So the thing is, it's going either up or whatever. Yeah. Oh wait, you also want the direction of the actor. Okay, this is bad. Oof. So it's along t hat, and t hat, because if it's rotating like that, then it's rotating like this. Sorry, it's a tangential vector is like that. Yeah. So negative t hat, that's where it is, right? So it's along this direction. But then r dot is negative, so actually it's along this right? So the positive version of r dot will be this thing. Yeah. What am I doing? So this is how much it is, and along that, yes. It's going along the meridian, yes, but is it going up or down? Because only knowing that can we actually figure out the direction. Okay, moves in the latitude 560 degree north. Okay, that's just the latitude. That's not saying anything about a direction. Along a meridian of velocity. I mean, okay, but along north or south? Tell me. I guess we'll have to make it into two cases in that case. Fine. First, calculate the magnitude. So, yeah, this little thing. And what is d phi upon dt? That's just going to be v upon r. Because, yeah, with v, it's going up or down, whatever. So, v upon capital R. Yes, that should be it. So, sine phi times v, that is the acceleration. And then, of course, what you actually want is this. So, that's r dot. That's not the acceleration. So, what you want is 2m omega naught and then v sine phi. And by the way, what is omega naught? It was 7.3 to 10 power negative 5, right? Yes. Then you got v sine phi. That should do it. Yeah. So 116, you got the magnitude. So the magnitude of the lateral force. That is, or you know what? Just gonna put force as it is. So force is just, and yeah, you just say okay, v is whatever velocity is along the north direction. So this calls in v north. Huh. Yes, nice. So this is a signed quantity. So 2m omega naught, the north velocity times sine phi, and then all of this is in the tangential direction. So t hat, and yeah, t hat is really just, I need to put that in there. T hat is equal to omega hat, so omega naught hat, sorry, cross r hat, right? So if you do that, yeah, you just get this thing. Yeah, that works out perfect. Right, this should work. Yes. So now once we got this, we'll calculate what this actually is. So this actually takes in the direction as well. So you don't have to do it in two cases. So this is f vector. The magnitude of f vector in this case is, or you know, just first of all figure what this out is, and you, yeah, what is the mass of this thing? 2000 ton. Wait, what is a ton? No, I don't remember it. I think a ton is just another 1000 kgs. So this will be 2 into 10 power 9. Sorry, 10 power 6 kgs. Yeah, let's do it. So 2 into 10 power 6. That times omega naught, which is 7.3 into 10 power negative. I think ton is 1000 kg, right? Yeah, of course. Okay. And then 10 power negative 5, that was the thing, the science. And that's what's omega naught. Not velocity, or doesn't matter. Velocity is given as 52 kilometer, oh come on, kilometer per hour. 3600, no, sorry, 1000 upon 3600 is like 10 upon 36, which is 5 upon 80. That times this thing. Which is like, this is 18 times 3, I think, so 324, yes. So this is going to be 15, huh? So this times 15 meter per second, yes. In that times sine phi. So phi is, it's 60 degree north. So sine phi will just be square root 3 upon 2. I just hate this at this point. Oh, come on. Are you serious? What dash? Fine. Fine. Calculated. This 2 cancels. Okay, this is just 30. So it's like 3 to 7.3 to 10 power 7 and 10 power negative 5, so 10 power 2. And then you got square root 3. Oh. Which is, so 3 square root 3 to 7 point, so 73 basically to 10 power 1. That should make sense, like 730. That's the force in newtons. And this big quantity is because the mass is very big, not that the acceleration is very big. We saw how little it actually matters, right? So it can't be that. I mean, I'm really not experienced with Coriolis force, so I don't know what orders to expect, right? What for the acceleration? Maybe that was just an error last time we got. Anyway, calculate what this thing is. So 3 times that is just 2190. Square root 3 is approximately 1.7. So it's gonna do this thing. These many newtons, and we'll approximate it in the end. So don't worry about that. 219 and then got 17. So 3 6 carried on. 6 carried on is like 7. 3 1 carried on. So 14 14 and 7.5 I guess. 0 to 19 3 2 1 carried on 7 and 3. So 3 2 sorry 3 7 2 3 and try to approximate. It's like this would be approximately 3.7 into 10 power. These many kilonewtons. Okay, kilonewtons is not used a lot. So I'll just say 10 power 3 newtons. Man, I wish I could use kilonewtons. Is it actually okay to use that? Whatever. 7.3 into 10 power 3 newtons. That should do it. So 116. Oh, okay, 116 is in the next page actually. Yeah. So the magnitude of the force is 3.7 into 10 approximately, of course, 10 power 3 newtons. That should do it. Okay, next 117, the last question, right? I guess it was the last question. Yes. At the equator of a stationary Earth body falls down from the height h is equal to 0. Assuming the air reactive negligible, find how much of the particle in what direction the body will deviate when it hits the ground. So yeah, good. This is actually something that I found in a paper while I was reading Coriolis force in detail, right? So I was just trying to verify if what I found out what's correct or not for the Earth, and they didn't have for any angle of projection, but for 90 degree they did have something, right? And we could use that, of course. So once again, the idea is the same. Just figure out our h and x, and we'll do it. We'll see what we get. Wait, didn't we actually? No, no. In that case, we actually didn't use the formula that I found. So yeah, we'll have to use it. So we'll just have h. X is 0 anyway because I mean we approximate it to be 0. Because it's projected up. So yeah, h as in this case is just half gt squared. Sorry, no, ut minus half gt squared. So what's u? We don't know. Whatever, just ut minus half gt squared. That should do it. And then yeah, like this is what's happening. This is r and this thing is h, and this whole thing is our small r in this case. Taking latitude angle phi, then this will be capital R plus small h times cosine phi. So the delta R thing is just h cosine phi. And then once again, all you just have is d squared c upon dt squared is equal to 2 omega naught, which is the angular velocity of the Earth, that times r dot. So dr upon dt, and then integrating that just get dc upon dt. So yeah, once again, no initial velocity because it's not there, right? Initially, there's no velocity normal to this meridian plane, so you don't have to worry about that. So this will just be equal to 2 omega naught delta r. Yeah, radius initially is there. Okay, it's not 0. There is a delta r over there. Fine, and that will just be 2 omega naught delta r. We just figure out h cosine phi, right? So 2 omega naught h cosine phi. And we just need to integrate what h is and we'll be done. So like ut squared upon 2 minus gt cube upon 6. That should, sorry, 6. Well, that should do it. And in fact, you know what? Let's just put capital T in it directly because that's what will give us the actual C value that we're looking for. So capital T is in this case just 2u upon g. So just put that in there and we'll see what we get. yeah, uh, this will be 2u cube upon g squared, right? So that 4 upon 2 is 2, and then minus, so first 4 upon 2 is just 2, and then upon 3 over there's like 2u cube upon 3g squared, I think. Anything else over here? No, it's, oh, okay, it's t, sorry, it's t cubed. What am I doing? It's gonna be 8 upon 2 is 4, so 4, and then you got u cube, yes, g cube, and then on the top is g, so g squared. So 4 third u cube upon g squared. That should do it. Yeah, that makes sense. Okay, so this will be what, 6 minus 4 is just 2, so 2 third u cube upon g squared. Why does it feel like this was different than, no, okay, this is correct because you will have to put it in this. So c is really just, yeah, now it matches up with what I saw over there. So this is correct. So 4 omega naught cosine phi is there, and then you got this integration of h, so that will just be 2u cube upon 3g square, and then times cosine phi. So there we go, 117 got a formula for that. Ha! Yes. How much of the vertical and what direction the body will hit the ground. So is that as it's going up, your well, the Coriolis force is related to the Earth. It's in this direction, right? It's coming out, so it's gonna go like, okay, and Earth spins where to, it spins from west to east or what? This is the west. This is the east probably. Okay, no, that's not correct. That can't be correct. When it's the morning, so if this is like at this point, you will have a morning. When it's completely opposite to us at that point, yeah. So you stand towards the sun. What am I doing? It's not supposed to be like that. Okay, and then you stand towards the sun. You do that hand pose thing. Man, it's so hard to visualize, but yeah, when you do the hand, oh come on, think. What is going wrong? Oh yeah, you should put your hand towards the right hand towards the sun. So if you are standing behind this, I mean this, the hemisphere behind us, right? So one is the one we are facing, and then there's other one, right? And then maybe the sun is over here or whatever, and we are assuming it's rotating like that. So then, god damn it. Think clearly. So, I mean, this is not physics. Why are they thinking about doing all of this? This is not like normal physics. It's something entirely different. Okay, you are standing normally, so you are, yeah, along capital R head vector, and then you have your right hand towards this, so then you are facing in this, this is the north pole, you're facing like that, and yeah, this is west, this is east for you, and yeah, and the earth is rotating like that. So what's actually happening is you are going from west to the east, right? And that's why it looks like the sun is going from east to west. So right, as we go like that, that's west. As we go like this is east. Sorry, no, no. This thing is east. So then if I continue like that, this will be east and this will be west. Man, this is so complicated. It goes from west to east. So this must be west and this must be east. So when it's doing that, what actually happens is that it's along negative t hat. So it's along the west direction. It's along that. And that is if we are assuming it's on the equator. If it's not, well, it's not exactly west, or what is it? West is not just, I mean, a position, no. Like North Pole, South Pole are positions on the earth, on the surface. But I think west east are more like, Yeah, that's how it's gotta be like that. Yes. So for each point, the west and east vectors along this meridian, they are the same, I think. That's how it should be, probably. This is scary. I don't even remember how it's supposed to be. I mean, okay, I never learned that. How do I even remember anything? But okay, let's go with it. It seems logical to me, at least. Not sure if this is actually west. Fine. Now, what do we want? 117. Yeah. So it's at the equator. Perfect. Then, of course, it's just west like that. Okay. Body falls down from the height h is equal to 500 meters. Okay. Assuming the air drag to be negligible. Oh no. Oh no. It's falling down. Uh-oh. Shit. This whole formula that we found out, it's for projectile motion with. Okay, so something else actually. Mm-hmm. Yeah, it's gonna be slightly different. Fine, it's still the same thing. Your h was whatever it was, and then this is how your h is changing. Yeah, and this is also probably just the radius, right? It's very close to that. So that little bit of difference won't make anything happen. That should be the thing. So in this case, your h is for some reason negative, right? I'm trying to integrate that. Oh yes, like delta r, that is now a negative quantity, so it's actually correct. So you can get rid of this thing, and it's just that. And the time period that you have to put in this, yeah, that is, wait, what? Oh, okay, this happens when you put time period as 2t, where t is the time required for it to fall. Yes, that should be the thing. Oh, okay. So complicated. So that ut term, that's gone. This is the thing, so just don't have that 4 right there, because it was like t cube or what? This thing, so then integrating that, just get gt cube upon 6. I is supposed to be t cube. So actually divide by 8. So this upon 6, that should be a thing. Right, that's what the integration of h will be. So now I'm just gonna do 2 omega naught cosine phi and all that stuff. So it's supposed to be u cube upon 3g and then 2 over here, because no, actually that's gone because 2 and 6 so goes away. This is so frustrating. I did all of that, and in the end it was not even the proper result. Now you got omega naught and cosine phi. That should do it. This is the actual thing, not this. This is for the complete projectile motion, and this is just half of the thing, right? So it's like 1/4. This is weird. Shouldn't be different. Why is it 1/4? Shouldn't this just be half of the thing? Yeah, it should be. Delta r is just, well, it's negative, yes. It's supposed to be negative 2 omega naught h cosine phi, and then negative h is just u cube upon all that stuff, right? Yeah. This is going in. It's supposed to be gt cube upon 6, and then you're gonna put t as that, just the time required for it to fall, which, okay, it's honestly just bad. The whole thing would be 2u upon g. Now it's supposed to be u upon g, where u is the final velocity. So in fact, we don't even want in u. Ah, what? Why is this like that? Yes. Well, at least now we know that it's gonna go to the west, right? Just write west over here. We actually need this thing. Sorry, we need that. Other than that, everything is cancelled. Where t is of a time required for it to fall. And what's that time gonna be? So So it's h up, right? So h, yeah, h is equal to half a t squared. So it's got half g times t squared. So t squared is equal to 2h upon g. What am I doing? What am I doing? Square root of that, then cube. Ah, it's a cube over there. It's not even a nice function. Are you serious? Such frustrating. Fine. Just figure out what this integration should be. Just g. Oh yeah, oh, this is just invest. So g, and then you got 2h upon g to the power of 3 upon 2. So it's like 2 square root 2 and h upon g to the power of 3 upon 2. And that upon, well, 6. So that 2 gets cancelled. It's got 3 right there. Square root 2 g upon 3. Yeah, just 3. And then this thing cubed. Okay, calm down, calm down. Going good. Once you got this, just gotta put 2 times of that and then cosine phi and all that stuff, right? It's gonna be 2 square root 2 g upon 3 that times omega naught and cosine phi. This is the answer. And this is pretty much just g upon 3 h up, so 2h upon g to the power of 3 upon, hey, this is actually nice because that cancels. Why did I not cancel it in the first place? So 3 upon 2, sorry, omega naught cosine phi, that's the answer. So now we can finally put that in there. Hope that it's correct. So, oh, and by the way, it's got g square root g over there, so you can just put square root g right there. Yeah. Oh god. Fine. It's got square root g, and then got 2h power 3 upon 2 upon 3 w naught cosine phi. This is our final answer. I can get rid of all of this and just put that in here. And this is in west. Yes. Let's calculate this. So h is given 500 meter. 2 times of that is 1000 meters, so 1 kilometer. Or you can, yeah, like that amount of 3 upon 2. Wait, what? 1000 power? Why? Why do you want 1000 power 3 upon 2? That's it. I'm not doing it any further. Maybe I should. Because like g can be approximately 10, and then maybe it's doable. Cosine phi, well, phi is 0. So get rid of that. Or just not get rid of that because this is more general anyway. Yeah. So phi is 0. Let's do it. Square root of 10 approximately, and then you got 1000 power 3 upon 2, like square root of 1000, and then that times 1000. Omega naught is just 7 point whatever that was, 7.3 into 10 power negative 5. Cosine phi is just gone, and that thing upon 3. So this is just 10 power 4 square root of that's 10 power 2. So 10 power 2 times 10 power 3 is 10 power 5. 10 power, oh, this cancels, perfect. So just 7.3 upon 3, these many meters, right? Yeah. Which is, well, 2.433 whatever, so 2.43 meters, that should do it. Oh god. Oh, okay, that's 7.3, sorry, not 2.3. Yes, this should do it. Yes, this should do it. Which is approximately 2. What am I writing? 2.43 meter west. This is it. So 117, we did it till that. I mean, these last 7 questions are just so not in syllabus that why would you want to do this? It's not even proper physics taught in, institutes. Coriolis effect. I never knew about this till now. Well, anyway, so the next section is going to be laws of conservation of energy, momentum, and angular momentum. Oh yeah. Fine. It's just got gradient and everything. Yeah. I'll explain what that is, but in the next video. Oof, it's gonna be long. So how many do we have for this? Or it just keeps on going, it doesn't stop. Okay, again this is bad. It's a lot of these. And then finally, after about reaching 200, you got universal gravitation. So that's when gravitation starts. Till now, it's just normal, basically rigid body mechanics and things like that. Okay, so I'll see you guys in the next video. Bye.